Hello, today we're going to talk about force. You can't talk about force without talking about Newton's laws of motion. Newton's laws of motion were published in the book called the Principia in 1687. And Newton came up with three laws that define motion of objects. The first law of motion is referred to as the law of inertia. And just as a reminder, inertia is an object's resistance to motion, and that value is directly related to an object's mass. Newton's first law says that objects at rest will remain at rest, objects in motion will remain in motion unless acted upon by an outside force. Okay? So it said basically, force is necessary for motion to change. That was the gist of his statement there. The second law is referred to as the F equals ma law, and this is how Newton originally wrote it in the Principia, was that A equals F over m. But that doesn't look as pretty in a textbook or on your paper as F equals ma, so most of the time you'll see that equation rearranged as F equals ma. But Newton said that the acceleration of an object is directly proportional to the force that's applied to it and inversely proportional to the object's mass. So as if mass is held constant and F is increased, the object will accelerate faster. If F is held constant and mass is increased, the acceleration will be less. Newton's third law of motion is referred to as the force pairs law. Sometimes you'll hear this as for every action there's an equal and opposite reaction. Well, that really doesn't do a whole lot for us. Instead, we can think of it in terms of a pair of forces. Okay? So if I have a box and I'm pushing on the box. Let's put a hand here. 1, 2, 3, 4, 5. So I'm pushing on the box. I'm pushing on the box with the same amount of force as the box pushes back on me. Okay? So forces always occur in pairs. If you hit a baseball with a baseball bat, the same amount of force is applied to the ball by the bat as the ball supplies back onto the bat. Sorry. So forces always occur in pairs. That's Newton's third law of motion. And those three seem very qualitative, but they are very important to more problem solving and the concepts that are involved with force. Let's talk about what a force is. It's anything that causes an acceleration. And we know from our study of kinematics, acceleration is when an object speeds up, slows down, or changes direction. And in order for any of those things to happen, there must be a force applied to an object. Okay? An object cannot apply a force onto itself. There has to be some force applied from some outside thing, either an electric or a force field or some contact force. We'll look at those in a second. Okay? Contact forces are forces that are applied by direct contact, and those are pretty common things you think about. You sit in a chair, you're applying a force to the chair's applying a force back on you. That's direct contact. Field forces are forces that are applied without direct contact. And we'll have three different types of those, one of which we will focus on most in this course. So field forces we'll look at first. We have electric forces, magnetic forces, and the one we're going to explore, gravitational forces. And these are all exerted. In gravitational forces, I should say, all objects that have mass exert a gravitational field. Okay, they have some kind of force field around them. And any object that has mass is affected by a gravitational field. So even you and the person that sits next to you in class, you have a gravitational field, the person next to you is affected by your gravitational field, so you are technically attracted to one another. However, both of you have such small masses that does not actually occur. Okay, the force between you is very, very small. So there's no real feeling that you're being pulled toward one another. So we're going to look at this point just the gravitational force exerted by the Earth, because it overwhelms every other gravitational force that we have on Earth because it is so massive. And later on in the semester we'll look at the equation that we get this value from, another one of Newton's laws, this time the Newton's law of universal gravitation. But right now we're just going to look at it in terms of a very small scale. And we're going to draw a free body diagram, which we'll talk more about later on. But a free body diagram is just a box that represents an object. So in this case, this could be a ball, it could be a car, it could be anything. But we're going to represent it with a box. And we're going to draw an arrow, a vector, that we're going to label with the force. So in this case, we have the force of gravity being applied to this object. Gravity always acts straight down. Okay, it doesn't matter what kind of surface an object may be on, doesn't matter if it's falling through the air or on the ground, gravity is always pulling the object straight down. And we're going to label our vectors with F for force and a little g that tells us it's the force due to gravity. Okay, so there is our first type of force, gravity. And force is a vector quantity, so direction is important. Keep that in mind. We're going to look at several different contact forces. The first one is referred to as the normal force. And the normal force, in this case, the word normal refers to perpendicular. Okay? Normal is just another word for perpendicular. It doesn't mean ordinary or average or any of those kind of things you think of as normal. It really means perpendicular. And this is a support force that is exerted by a surface onto another object. Okay? It acts perpendicularly away from the surface onto the object that's resting upon it. Okay? Normal forces, there is no universal equation for it. It changes based on a given situation. One very common example we'll have is an object on an incline. And if we set up this object on the incline here, the normal force is going to act on it perpendicular to the surface. So if here's our surface right here, then our normal force has to be perpendicular to it, and it is acting away from the surface. Okay, so there's our normal force. Let's go ahead and label our other force acting on it as well, which is gravity. As you see, gravity is straight down to the center of the earth, not down into the surface, toward the center of the earth. Okay? Normal forces can be supported by things that are horizontally. If you're pushing an object into a wall, the normal force can be pushing back out onto the object from the wall. So it doesn't necessarily has to do with an object's weight, it is just a support force. Another contact force is friction. Friction is very common. This results from the interactions between particles on the atomic and subatomic level. So you have those objects that are coming together. Sometimes it's electrical charges. Sometimes it's just the shapes of the objects and how much they're attracted or repelled by one another. Friction always opposes motion, and it depends on two things. It depends on the coefficient of friction and on the normal force between the two objects. Okay, between the surface and the object, I should say. Our equation we have for normal force, frictional force, not normal force. Remember we said normal force does not have an equation. But our equation for the frictional force is that FF, so force due to friction, equals mu, which is the coefficient of friction, times Fn, the normal force. Okay? So mu is a value that is unique between two different surfaces. Generally it's less than 1, but it does not have to be less than 1. And that is something that we could see between those two different objects. Okay? The higher the mu, the higher the friction, the higher the normal force, the higher the friction. So you have a heavier object, sometimes it's harder to move it because the normal force between it and the surface beneath it is greater. We have two different kinds of friction. We have kinetic friction, which is friction that opposes an object while it's moving. And we also have static friction, which is friction that opposes motion before it begins. Static friction is always greater than kinetic friction. Okay? And think about when you're a kid and trying to rearrange your room and you have to move your dresser or your bed and it's pretty heavy. It always requires more force to get an object moving than it does to keep it moving. And that's how you can think of static friction being greater than kinetic friction. If we looked at it on a free body diagram, we'll just look at it here. We know that it has to be on a surface in order for friction to be present, unless we're talking like air resistance. And I like to draw my frictional force on the surface there. Okay, so we see where it is acting. The other forces we'd have here, of course, would be gravity and the normal force. Oh, goodness gracious. Okay, and there does not have to be an applied force for an object to be affected by friction. In this case, you see no horizontal forces acting otherwise, right? So if there's friction acting on it, that means the object must already be in motion. Okay, so like pushing a book across the table. there's an initial force that you apply to get the book moving, but then friction is going to slow it to a stop. And there's no applied force during that time once your hand comes off of it. Another contact force is an applied force. Okay, this is just a push or pull. We'll label it on a free body diagram as an FA. Okay, so in this case we have gravity acting down on it. If it's on a surface, great, we'd have a normal force. If it's not on a surface, there is no normal force. Okay, let's just say that it is in this case. We'll go ahead and say that there's a normal force. And let's say we have an applied force horizontally. If there's a frictionless surface, then there is no forces opposing it. But if it is on a surface that is not specified as being frictionless, we have to assume that friction is present. Okay, that's something that you have to always keep in mind. Friction in the real world is always present. But here in Fantasyland physics, we can say that we sometimes will have frictionless surfaces, and in that case, we would have no force of friction. Another contact force, and this will be the last one we'll look at today, is the tension force. And this is the force exerted by a rope, wire, or string. And a very common example of that is something that's being lifted vertically, okay, like an elevator. And if we draw a free body diagram of an elevator, we would have the force of gravity pulling the elevator down and the force of tension acting up. Many students want to draw a second force for an applied force, okay? The applied force, of course, is happening up here somewhere, probably like a winch, you know, pulling up on a string. But the key here, guys, is when you draw a free body diagram, you're only looking at the forces that are directly applied to the object in question. So in this case, our elevator. The applied force up here is not directly applied to the elevator. It's applied via the rope, wire, or string. So we have to only include this as being the FT, not as being an FT and an FA. Okay, if you want to call it FA, that's fine, but FT is technically more correct. Okay, there is no universal equation for force of tension. Again, it could be different. It changes based on the situation, and you'll get that when we do something called summation equations later on. The last thing we're going to look at today is the units of force. And force is something that we use very common, so we're going to have a derived unit for it. Okay, F equals MA, we'll write it here because this is where our units will come from. If we think about our SI unit, instead of the metric base units, our SI base units, which are the ones that the International System of Units sometimes called MKS units. Our base unit for that and for mass is the kilogram and not the gram. And the reason the kilogram is the base is because a gram is very, very small, and it takes a lot of grams to make up any significant amount of mass. So instead of the base unit being grams, it's kilograms. We already know our base unit for acceleration, and that is going to be meters for the length unit and seconds for the time unit. So meters per second, or meters per second squared. So for force here, we have kilograms times meters per second squared, and that unit right there is called, or defined to be, a Newton. Okay, in honor of Isaac Newton, of course. And we use a capital N to represent newtons. So 1 kilogram meter per second squared is equal to 1 Newton. If you divide newtons by kilograms, you're left with meters per second squared. And if you refer to your equation, you're dividing force by mass. So you know that should be an acceleration unit. If you divide newtons by meters per second squared, you're left with mass, which is measured in kilograms. So your units do make sense there. So make sure you pay attention to that and know what that derived unit is. And that's our basics here on force. We'll get into some more specifics later on. Thanks!